Okay, so the next category is, I think we're going to do biggest whoopsie for 2020. Our nominees are Cyberpunk 2077, the meat question from last week's episode.
Meat question wins.
Yeah, okay,
meat.
Good talk.
Always meat.
I mean, look, if you look at the shortcomings of the previous meat question and you see how they've improved over time. I mean, I realize this is not most improved whoopsie.
Look, this is the hill I'm ready to die on, Brad. I think that Cyberpunk.
I can't do this.
How are you doing, man?
I cannot do this. I'm good.
You've been doing too much podcasting this week, Brad.
Yeah. It's going on hour 26 here. Let's get this going. How are you guys doing? Doug's still driving a robot a chunk of the way across the solar system. That's still a little bit more momentous than what I've been up to.
Better than both Cyberpunk and eating your own thighs, yeah.
Probably more responsive, at least.
So this week, well, I guess, should we cold open or should we start the show?
Let's just keep going.
Okay, at this point.
I think it's fine to flip the table on the format this week.
So this week we're joined once again. Well, if you're a patron, you have met Doug before, but if you are not, this is your first time meeting Doug Ellison of JPL, who is a camera op on Curiosity and has been for a while now, right?
That is what I do, yeah. 4 years of taking photos on Mars. I've taken about, I think I did the math, 14,000 pictures on Mars, something like that.
Look, that's about what you take in 1 year when you have a new kid, is my experience.
Yeah. So for at least the first year of our kid, it was about the same.
He said 14,000 photos, and I almost went straight to the Flickr joke, and then I was like, nope, we burned that one on the last episode. So let's just keep going.
So we asked Doug to come back and talk to us because in a couple of weeks, the next Mars rover in I think it's the 5th, probably at this point, American Mars rover.
Yes, it'll be the 5th. Yeah,
is landing. Hopefully, if everything goes well, landing on Mars in a couple of weeks after about a 7-month trip. And we just thought it'd be fun to talk about that and talk about what it's like to drive a 800 to 1,000 pound vehicle around Mars, drilling rocks and taking pictures.
It's February is going to be busy. There's a whole kind of fleet of spacecraft. We have these windows every 26 months, and no one really missed this window. So we have a Chinese mission that gets there in a couple of weeks' time. We've got a United Arab Emirates mission that gets there in February, and then we've got Perseverance, the new rover, landing on February the 18th, lunchtime Pacific time, down to the minute. We can tell you when it's going to be. It's at 12:38.
How much collaboration is there between the different international space agencies? I mean, I know, like in the political realm, there's a certain competitive aspect to it, but like scientists like just share knowledge, right?
So almost all these missions end up sharing every single piece of data they take with the wider scientific community and thus the public through various websites and stuff. Like you can go and download data from all of our Mars rovers. You can go and download data from China's moon rovers, right? Like it's all out there because that's the right thing to do. And I think all the science community around the world know that. But there are legal repercussions between NASA collaborating with China. It's tricky. Politically, we're just not allowed to do it. And so they're somewhat on their own. China does collaborate with the European Space Agency. NASA collaborates with the European Space Agency. The Emirates mission has definitely got some US involvement. It's using the Deep Space Network, which is NASA's network of ground stations around the world to talk to us. And so I mean, most of these missions end up being international in one way or another, just by virtue of not one place has everything it needs to do the job.
I think there was one planned mission for this 2021 window that missed, which was the ESA Russia collab, right? Yeah, so it would have been a Russian lander with a European rover, Rosalind Franklin. Unfortunately, they just weren't quite ready. And so the frustrating thing is that you can't say we'll go next week. That you have to say we're going to go next window, which in this case is 26 months later. People in glass houses, because Curiosity was 2 years late. The InSight lander was 2 years late. And so it happens. And no one wants it, and it's really frustrating when someone has to make the call and go, you know what, guys, we're just not going to be ready. And suddenly you've now got to find a way to keep your entire team busy and occupied and trained and happy, all the way for those 26 months whilst you fix whatever often quite small thing made you miss your launch window. Can you, at that point, can you like pull, I mean, I assume if they reached a point where like the rover is on a pad ready, with a rocket underneath it, you're probably not going to pull it back into the lab and start adding stuff or removing stuff to it at that point.
It's very, very small changes. A lot of the changes will be like we had some placeholder components and the finished ones weren't quite ready, and so it's kind of swapping out for like mocked up parts for real parts. Sometimes it could be flight software not ready. The good thing about flight software is as long as your vehicle's happy once it's in space, you can always send your flight software late at the speed of light. But
hold on, are you saying that there's day zero patches for spaceships?
We have fixed bugs in Curiosity's flight software on several occasions. In fact, because Curiosity and Perseverance are very, very similar, they kind of their flight software started life in about the same place. And Perseverance's team have found flight software bugs. They've handed them on down to Curiosity and said, hey, we found this bug in the flight software. We think it might apply to you as well. And then we've gone, you know what, that's a bug that only happens during landing. We don't care anymore. Or actually, that could bite us at some point. Let's do that as a fix. And then we'll roll all those fixes up into a new flight software build that we will send to the rover over a period of a couple of weeks. And then literally it will build the image on board and then we'll boot up into it.
Wow. I was working on
other planets. Holy crap!
Yeah, I was working on a cyberpunk joke there about maybe the thing the games industry could learn from NASA is not to ship stuff until it's ready. But then I'm going to just leave that one aside.
I like the Spirit and Opportunity rovers, which went in 2003 and landed in 2004. They launched without any software that would allow them to have driven once they landed. It was all sent between launch and landing because you've got kind of 9 months of fairly quiet time with the vehicle. And so that flight software they spent more time developing on the ground, they sent it late, basically.
So when we had you on for the Patreon episode, we talked a little bit about the hardware on these rovers being... I mean, it's cutting edge for space technology, but it's a little bit archaic for terrestrial tech, right?
It's a little, yeah. It's so Curiosity and Perseverance is a very, very similar vehicle. They both use what's known as a RAD 750, which is a 133 megahertz power PC chip. It's basically a low spec first generation iMac, the ones that look like goldfish bowls. It has 128 meg of RAM. It has about 4 gig of flash. Curiosity, all of our engineering cameras, what we use to kind of get the lay of the land, have a look around, figure out what we want to go and look at more closely, are all 1 megapixel and black and white. They actually started life for a project that was due to fly in 2001. And so they're, 20-year-old design at this point. Perseverance gets a big upgrade for that. Its engineering cameras are actually 20 megapixels and color, which is going to be amazing. Those are going to look... I saw some images taken in the clean room, and I swore out loud and went, good God, that looks like a photograph. As opposed to the typical potato cam crappy space pic. They just looked like, someone had taken a cell phone in there. But generally speaking, yeah. But the operating system is kind of a real-time operating system called VxWorks. Things like the 787 Dreamliner run on that. Things like the Asimo robot run on that. And it's enough. I mean, more computing power would be nice for Curiosity. The most computer-intensive thing we ever do is visual odometry, which is kind of when we're driving, we look at the terrain around us, figure out exactly how far we've moved, compare that to how far we think we've moved, and then we can figure out if we're slipping our wheels and stuff like that. And when we're driving with that turned on, we're actually only moving about a third of the time. 2/3 of the time is just sat there crunching numbers. What they've done with Perseverance is throw in another board that basically has a dedicated chip for things like visual odometry. And so the pause to analyze the imagery basically goes away. So it kind of triples how far it can drive in any given day, which is a huge upgrade.
That is like, it's funny, the things that gate, from talking to you and other folks from JPL and folks who've worked on these kinds of rovers, it's always stricken me how the things that you wouldn't expect are the things that gate. Like on Curiosity and Spirit, it was, what the solar cells, the amount of electricity the solar cells could generate during a day, a lot of times, and how much the batteries could store and stuff like that. But I never would have considered that like compute is the thing that is holding back Curiosity in terms of miles per day.
I mean, Perseverance has a stowaway on board, which is the Ingenuity Mars helicopter, and by a huge margin, Ingenuity carries the fastest CPU ever sent to Mars, because inside it's actually a kind of derived from a drone dev kit. That's correct.
Really?
Yeah, it's a drone dev kit inside with a whole bunch of mods, but it's an ARM CPU in there, and in fact, I think it's 2. And
do they have to shield it? Like, do extra shielding and stuff around it because it's, or is it?
There's kind of a like, if you've got a CPU sat in deep space for years and years and years, you're going to get hit in such a way where at some point you'll have a bit flip that's bad, right? And so you need a machine that's robust to that. With the helicopter, they figured out that if that happens, they can reboot it so quickly it doesn't matter. And so it has, and people can look this stuff up. There are PDFs that detail how this thing has been designed, how it's built, you know, what the flight computer is, what the backup kind of watchdog computer is, and stuff like that. And so it can, so for like recognizing features and images and figuring out exactly where it's going to fly, they've got that faster CPU. For the basic housekeeping and keep it in the air if something goes wrong, it's a little low-level thing. And so you kind of get around it that way. And it is only a tech demo, you know, so if something were to go wrong, it was a demo, it didn't work out great. A bit like the old Sojourner rover in 1997, that was kind of a tech demo. Can we drive on Mars? The answer is yes, and everything that's followed has been a child of that. This Ingenuity helicopter is kind of the next generation of that. Can we fly on Mars? And there are people already thinking, well, if this works, you know, what science instruments can we bolt onto something a bit like this in the future?
Can I just want to clarify, when you say helicopter, we are talking a literal helicopter with rotors, and that's not like just a fun colloquial name for something that is not actually a helicopter? I mean, because, you know,
a real helicopter. It weighs
not a lot of air on Mars. I just want to make sure.
It's like take a plane up to about 100,000 feet and stick your hand out the window. The air is about 1% as thick as ours. And you might think that's not enough for blades to grab a hold of, but in terms of the energy required to get it off the ground, it's about a third of what it is on Earth because the gravity is about a third. So gravity is going to help you a bit. And as long as you don't spin rotor blades fast enough that you kind of, the tips of those blades are traveling supersonic, you just need more aggressive rotor blades and a light enough vehicle that you close the engineering problem. And they've done it. There are videos of them flying a mass kind of an adjusted version of this helicopter so it weighs about as much as it will on Mars in one of our vacuum chambers with just enough carbon dioxide put back in it to be Martian atmosphere, and it flies.
Wow.
It's absolutely extraordinary.
I mean, I have to imagine it's always interesting to see real life tech that we use here on the planet going into space and like putting drone controllers and stuff like that, or modified drone controllers, whatever, on something like this is really nifty. So this one doesn't have science instruments. This is basically proof of concept. Cameras, really basically.
I think it's got a little downward facing camera that it uses for kind of watching the ground beneath it, for the kind of tracking the where it is, kind of like an optical mouse, just a little bit higher. And then it's got a kind of perspective camera that sticks out the side that goes from kind of just about the horizon to almost directly below it. And that's basically going to generate really nice postcards that are geologically useful. I mean, they're like, okay, we have this gap in our understanding of the terrain around us. You've got the rover eye view that's from about 2 meters up. You've got the orbiter view that's from 400 kilometers up. It would be nice just to pop your head over a hill and have a look, you know, and bridge the gap between the orbital data and the rover data. One could envisage in the future, like the helicopter scouting out ahead a few days in advance. From that data, you generate much better maps of where you want to go next. And then from that, you can therefore plan longer drives with the rover because you now know what's over that next ridge at a scale that's useful for rover safety.
How I assume that this is going to be piloted in the same way that the rovers are, where you say, hey, take off, fly 100 meters this way, take some pictures, and then fly back and land back on the rover?
So the rover's actually going to drop it onto the ground and then drive away and literally park like 100 yards away. It's going to get the hell out of the way because, you know, little helicopter with big flappy blades spinning around kicks up a lot of dust, and dust gets on things like lenses and stuff. So they're going to park pretty long way away from it. And then it has its own little solar panel so it can charge itself. And I think they've got about 5 test flights planned. So one is literally pop up, hover, drop back down again. One is pop up to about 5 meters, fly 5 meters one way, 5 meters back, pop back down again. It's not smart enough to find a safe place to land. So what you do is you say, this is a safe place to land. It can take off and then go and land there. But it is rover-like in its kind of autonomy. It can look after itself on the second-to-second basis, but it's only really going to do what we've told it to do.
It doesn't have any like blade guards or anything like that. And it looks like it has carbon fiber blades. So
they had a set of those blades at an open house a couple of years ago, and it is uncanny how light they are. They are.
Oh yeah.
They feel like nothing in your hand, but they're huge. I mean, they are about a meter across. I mean, they're absolutely extraordinary.
It's funny. The thing it reminds me of is those human powered helicopter flight demos that like Caltech kids do.
Yeah, it's the same problem. It's you don't have enough, they have very little power and so need gigantic blades to generate the lift. This needs gigantic blades to generate the lift because there's not enough air, and it's as long as you don't break the speed of sound with the tips of your rotors, you're fine. And they just have super aggressive airfoil shapes, especially kind of inboard on those rotors. They're very, very aggressive propellers. And I mean, it worked in the vacuum chamber. Everything says it should work when it gets to Mars. Fingers crossed. Yeah.
Oh, sorry. Go ahead.
Oh, go ahead, Brad.
This may be a very rudimentary or ignorant physics question, but is the speed of sound impacted at all by the extreme difference in the air density?
It's different, but not hugely.
Okay.
It's the same ballpark. And so it's always confusing when people talk about the spacecraft hitting the top of the atmosphere at Mach 25 or something. It's like, which Mach do you mean?
Earth or Mach or Mars?
But the effects of being supersonic or transonic are at Martian levels, not Earth levels, obviously, because Mars doesn't give a crap what the speed of sound is on Earth.
That makes sense.
So I'm just gonna ask a question that Will actually wrote in these notes. I hope he doesn't mind. But
no, go for it.
One of the things he has written here is, why are we sending so many rovers to Mars? I mean, is that mostly just about proximity, like ease of getting it there? Or I mean, obviously, like we talked about this some in the Patron episode, like Mars has a fascinating story and mystery to figure out in terms of, where all the water went, was there life there at some point, et cetera, et cetera? Like, what are the factors there as far as you see it?
There is an overriding mantra when it comes to exploring planets that is flyby, orbit, land, rove, and return samples. And you try and do the ideal situations. We go and do that in all of the places, right? We go and do that at Europa and Titan and Mercury and Venus. And Mars happens to be pretty close. It happens to be enough like Earth that it's fairly easy, not trivial, but fairly easy to land on. You can get lots of data home from it. And we have this understanding that long ago it was an awful lot like the Earth. It had running water on the surface. There were all the ingredients that life needs. We don't know if there was life there, but all the ingredients it needs were there. And so in terms of the hunt for life in our cosmic backyard, it may not be the absolute best candidate, but it's the nearest good candidate. What we'd love to have is some gigantic submarine with a huge lab inside it, swimming around the oceans of Europa, or sniffing its way through the vents that spew out the bottom of Enceladus, or wading through the lakes on Titan. But those are all much, much bigger challenges. And so in terms of, what is the fruit with which we can currently reach, roving around Mars, understanding its geology, understanding its habitability, understanding the potential astrobiology of Mars is what we can reach right now. But as our technology improves, that list of flyby, orbit, land, rove, return samples gets further and further from Earth. And so we have plans for a Europa lander, which would be amazing. And then eventually at some point, maybe there is a Europa drill that starts drilling down into the surface to understand what's going on down there. And we have, amazingly, a quad rotor helicopter that's being, it's actually been selected. It's a properly selected mission that's going to happen. Going to Titan, it's going to fly around Saturn's moon Titan.
Wow.
Yeah, that's going to be pretty special. It's and so we, as our technology improves, we push the boundary out of doing all of these cool, interesting things.
I realize this is a big question. I'm not asking you to commit to anything here, but do you think we will see missions like that actually taking off in our lifetimes, or is that a period of like multiple decades of R&D to even think about trying something like that?
I think landing on Europa definitely within our lifetimes, and I think burrowing down the 10 plus kilometers of ice to go and explore it with a little robotic submarine is probably a little further away.
Sure.
I think that's a big ask.
That's a lot.
It's really hard. And
can't you just put a heating source on something and just warm it up, just let it melt through, or
sink its way down there eventually?
It freezes behind you.
Oh, right. Yeah.
Space.
No
You've got an answer for everything.
Yeah. And so you need some sort of lander, and then you need some sort of thing that penetrates through from there. The radiation environment on the surface of Europa is an absolute horror show.
Is that because of Jupiter, or is that
Europa? Okay. Yeah. You're trapped kind of within. I mean, the biggest thing in the solar system is Jupiter's magnetic field. It stretches all the way to the orbit of Saturn. It's enormous. It is so powerful. It generates currents that flow around the crap being blown out from Io. There are kind of eddy effects. It's a horror show. Like the Juno spacecraft that's orbiting Jupiter right now, the electronics are literally in something called the Vault, that is like this 150 kilogram titanium box to try and protect it from the worst of the radiation. And even then, it only spends a few hours every kind of month close to Jupiter. And then its orbit takes the heck away from Jupiter, so it can then send all that data back home again. Because it's a nightmare. It's an absolute nightmare. No electronics like it.
And I mean, I guess one of the other things we talked about this a lot in the other episodes, so I don't want to dig in too much, but I mean, Mars also, we have a lot of infrastructure there kind of compared to the other places in the solar system, right?
We do. We've been visiting it with almost every opportunity that we can for 20 years or so. And so we have a fleet of Mars orbiters that act not just as kind of scientific platforms in their own right that help map the planet, understand the planet, find us the cool places to go and, land and rove around. But they act as relay satellites as well. So Mars Odyssey, Mars Reconnaissance Orbiter, MAVEN, the European Trace Gas Orbiter. We speak to all of those. Even Mars Express, which is an older European orbiter as well. We use those as relay satellites. Mainly it's just the Mars Reconnaissance Orbiter and MAVEN, and the European Trace Gas Orbiter for Curiosity, because they have the newest, shiniest versions of the radio, so we can get more data home that way.
What's a good throughput tomorrow? Like if I'm ordering DSL in the Planitia crater, what am I getting?
So yeah, AT&T run out to Gale Crater gets you your daily cap is about something between 500 and 1,000 megabits per day.
Okay.
Call it
divide that by 8.
Yeah, call it 100 to 200 megabytes a day. It's not, extraordinary. It's pretty normal. When we landed, when Curiosity landed in 2012, MAVEN wasn't there. The European Trace Gas Orbiter wasn't there. And so it was relying on 2 pretty old spacecraft. And so Curiosity actually is getting more data home on a day-to-day basis now than it ever has before.
New data plan.
Yeah, right. Yeah, free upgrade. And so that's kind of one of the reasons that the Perseverance rover could say, well, screw these crappy old 1 megapixel black and white cameras that were designed in the late 90s. Let's have some new engineering cameras that are 20 megapixels in color, because now we have the data volume to return that stuff home again. And so they knew that, the better infrastructure was there when designing Perseverance. We didn't know it was going to be there when we built Curiosity. And so they're going to make the most of it.
So that kind of brings us to one of actually probably the thing I'm the most excited about with Perseverance, which you talked about on the other episode a little bit, which is the kind of landing home movies that it's going to be sending back to us of its entire landing sequence once all that is done and recorded and everything. I mean, I've got 100 questions about that. Are the engineering cameras that you just mentioned, I assume those are distinct from the landing cameras? Are the
they are.
cameras that are going to be used for the landing? Are they going to do the landing and then go inactive from then on? I mean, I guess you guys kind of use everything you can, but
so during landing, like the engineering cameras interface directly with the flight computer's board, and you don't want to basically give the flight computer anything else to do while it's landing, generally speaking, because it's kind of busy. And so all of the name is EDL, entry, descent, and landing. All the EDL cameras are actually controlled by their own board. That literally interfaces to some of them through like a USB 3 bus. It's crazy. And so we have a couple of cameras on the back shell that will take high speed of the parachute deploying. That's never been seen on Mars before. We will have a camera on the sky crane. That's kind of the rocket backpack that carries the rover down to the ground. A camera on that looking down at the rover. A camera on the rover looking back up at the sky crane, and then another camera on the rover itself looking down, much like the one that took the only version of the only camera angle we had in 2012, which was a 4-ish frame per second color landing movie at roughly HD quality and color. And so all of those different camera angles will document all the important parts of landing, all the way from parachute deployment, heat shield deployment, rovers, dropping out from the back shell, the rover separating from the sky crane, the touchdown, and then the sky crane flying away. And there'll be a microphone to record sound throughout all of it as well. And so the supercut of that is going to be just amazing. And they're all good enough to be like 720p-ish. Some of them are a little bit better. Some of them aren't much better than that. 2-ish megapixels are kind of the lowest end ones. But to be able to see it from so many different angles, to understand, there's the outreach side, which is, it's going to look freaking awesome, right?
Yeah.
But then there's also the engineering side of, we think we know how this behaves. We've seen it through telemetry in the past. Exactly how did it behave? We've simulated trying to deploy parachutes at those environments. What's it actually going to be like when you see it deploy on Mars? That kind of thing.
This is the fascinating, the idea that we don't know how a parachute opens. Like, we have a pretty good idea how the parachute opens on Mars, but we have no confirmation that it actually is working the way we expect.
Nobody's ever seen it. Like, maybe Mars fairies materialize out of nowhere and just waft the rover down to the surface on
sky hooks the whole way down.
So like golden chariot.
Like, Curiosity tested its parachute in the world's biggest hairdryer, the 120-foot wind tunnel up at Ames Research Center in the Bay Area. Mm-hmm. And what you do is you say, okay, we're going to be doing this in a Martian atmosphere at Mach 2. Roughly speaking, how many molecules of air is that per second, right? What's the dynamic pressure of that? And it turns out it's like a strong breeze in the 120-foot wind tunnel. And so you literally, like, the NASA engineers, when they did this with Spirit and Opportunity as well, they said, hey, can we deploy a parachute in here? And the guys at Ames like, we've fired jet engines into here. Do what the hell you like. It's fine. So the static load from that deployment is about right. But on Mars, you're doing it with thinner air, but at a supersonic speed. And so it snaps open really quickly. But it's the same number of molecules hitting at the same time. So the dynamic pressure is about the same, but the speed of that air is much higher. And so our understanding, and this, when I was doing education and public outreach, I worked on the Curiosity landing animation, and we tried to make it, look real. They say that actually you get this initial snatch as the parachute reaches the end of all of its cables. It kind of ripples for a second, and then it just snaps open almost instantaneously. And you get this massive jolt off the back of the spacecraft. Like, it pulls like 60,000 pounds of force, right? It's huge. And you pull 12G, for a few seconds while the moment that parachute's inflated. There were a couple of research programs, one called LDSC, the Low Density Supersonic Decelerator Program, but then also Perseverance project itself went and said, let's just fly some rockets up to a couple of 100,000 feet and deploy parachutes out the back of them it's a more Mars-like environment, is at the right kind of speed, the right kind of atmospheric density, 100,000 plus feet up in the air. Mm-hmm. But it's nitrogen and oxygen, it's not carbon dioxide, and gases behave differently. And so it'll be nice to see, exactly what goes on when you try and deploy a parachute at Mach 1.8-ish at Mars.
Few dissertations written about the stuff that comes out of this, probably.
Yeah. How much of that stuff gets actually published? And like, NASA has a technical report server, JPL has its own technical report server, and you can do Google searches like Mars parachute, just add PDF on the end, and you'll get a bunch of the reports that are published about how well these things perform.
I assume somebody's crunched the numbers at this point. I mean, you have a rough idea how long the landing sequence will take, and times X number of cameras and microphones. Like, do you know what the total quantity of data is going to be of all those recordings, and how long it'll take to send back?
I don't know. The only thing I have seen is that it'll take some weeks to get it all back. Okay. What they will do is trickle it out of the board that was controlling those cameras during landing and storing all that data. They'll trickle it over to the flight computer in chunks, and then it will come back home like normal data. It could take a while. Like, it took a couple of weeks for Curiosity to send back that landing movie, and this is going to be 6 times worse.
Sure. I feel like you managed my expectations pretty well on the last episode, because I was very excited about the idea of recording video on another planet, until you pointed out the video will essentially, well, at least once they're on the ground, will essentially be just like still photography, because there's not exactly a lot of tumbleweeds on Mars.
Very would a video on Mars be discernible from a still image. We do see stuff move. We see things like clouds occasionally overhead of the Curiosity. We see dust devils blowing by. Occasionally occasionally when we look for dust devils, we actually get a little bit of the rover in one corner of that image, and we'll see like there's a fabric cover over the back of our power supply. We'll see that blow backwards and forwards in the breeze. And when we take movies with Curiosity, like they're a frame every 12, 15, 20 seconds or so. So they're not really movies, they're kind of more time-lapse. But like a couple of months ago, we saw a big-ass dust devil about half a mile away, just waft by over a period of 4 minutes. This thing was like 8 meters across, 50 meters tall, about 600 meters away, and it just sat there, was just spinning its way past us. It was awesome.
Wow. So one of the things, I mean, it is disappointing that there won't be a Twitch stream of the landing from the rover's perspective. I got to say, if we could work on that, that would be great.
We'll get right on that.
Yeah. What up, operators? It's your boy Perseverance here.
Don't forget to like and subscribe.
Yeah. This is slam that like button.
XX Perseverance 420XX. Yes.
Yeah. Doug, there's a bunch of new science stuff. Like this is the history of this rover is that it was why build one when you can buy two for twice the price, the famous Jodie Foster / Carl Sagan contact line. But this was one of the twins that was made for Curiosity, and then we've spent the time intervening, upgrading and adding new science and taking the lessons we learned from Curiosity and making this rover better, faster, stronger.
Other adjectives as well. So the rover itself, I think, is new. If you put them side by side, you'd struggle to tell them the kind of the chassis apart. I think Perseverance is slightly longer by like an inch or two. It's a little bit bigger, but as a design, that only a parent would be able to tell them apart in terms of what the chassis looks like. It's a little bit heavier. It's got a bit more stuff inside. The wheels are a big upgrade. So we've learned a whole bunch about what Mars likes to do with thin aluminum wheels. And so Perseverance actually has slightly narrower wheels and less kind of angular tread on those wheels, and so they've tested those to destruction, and they're like, there's nothing Mars can bring to the table that will hurt the Perseverance wheels,
because the Curiosity wheels had like there was concern that they were going to wear out before the rover was done with the science, right?
They look horrific. They've got holes in them, some of which you could probably put your hand through, but they still work, and they work absolutely fine. In fact, we could shed the inner 2/3 of one of our wheels, and in terms of driving around, the rover don't care. So, and there are papers published about how exactly we would do that if we had a wheel that was so damaged we actually wanted to get rid of it. You'd try and kind of peel it like a tin can against a big rock and shed it in some way. But I believe the Sky Crane, the rocket backpack that lands the rover on the ground for Perseverance, is the engineering model from Curiosity. So that's like legit leftover bits and pieces. I'm sure there are some spare electronics boards. I know that the Perseverance team has been borrowing some of the testbed hardware of Curiosity because they're very, very similar for doing flight software testing and stuff like that. The big upgrades are in what Perseverance is designed to do, which is to identify, collect, document, and then save and then dump somewhere really well documented samples that are going to get returned to Earth. It is the proper first step in a coherent Mars sample return program. It's the ultimate goal. That there is no amount of science or engineering that we could do to put the best research labs on Earth on Mars, because if you put it this way, the samples that were brought back by Neil and Buzz 51 years ago from the moon, the best science being done with all those Apollo moon rocks is being done right now, because better instruments, better laboratories, better techniques have developed now than there were last year or 10 years ago or in 1969. And so the very best science we'll be able to do in understanding, the history of Mars, its habitability, maybe present or past bacterial life or what have you, is by bringing bits of it home. So what amount of bits are we talking about here? Like a couple of ounces per sample or grams? So it's got about 40 or so of these kind of coring tubes on board. And each one, when you drill into a rock, it collects a piece of rock about the size of like a Sharpie, something like that. And the hope is that we'll return a couple of dozen of those back to Earth. And so there is a meeting that actually the public could dive into, amazingly, where they're trying to figure out the exact strategy of, if we see something really good, should we take like two of them and save one and dump it somewhere else and save one and dump it here kind of thing. Because in 2026, another rover's got to come along, pick them all up, drive them back to a lander that's got a rocket on it, shove them in the rocket, and the rocket's got to then take off from Mars back into orbit around Mars. Then a gigantic Mars orbiter's got to go and find that, rendezvous with it, stick it in an entry capsule, and leave Mars and come back to Earth. And the kind of the systems engineering, like kind of the architecture of, okay, we're going to be driving around. Not all the good science is going to be in the same place. So do we collect a bunch of stuff and then dump it in one spot? Do we take two of everything, dump one set here, then drive somewhere else cool, collect a whole bunch of stuff and dump another set there? And then when it comes to, that fetch rover in 6-7 years from now coming to collect these, decide which is the best set to go and get? You could
just hold everything and hope that you find a good place to drop it.
You could say, let's make sure we hold on to something, because if, for example, that fetch rover doesn't work, well, Perseverance could then drive over to where the lander is, drop them there, and the lander could pick them up and put them in the rocket. So the risk posture of that, when you have very limited results, like you have X number of tubes and you can only get Y number of tubes home, is really interesting. It's a fascinating problem to try and solve.
Could you even venture a guess at the value per ounce of that material once it gets back here? Again, it's like it must be in the billions, right?
Let's very roughly ballpark this. The Perseverance is about $2.5 billion. The Fetch rover and the lander that will take it and the little Mars ascent vehicle are probably going to be, when you add them all up, very similar value. And the European Space Agency is actually going to build that little Fetch rover. It's going to be more like the size of Spirit and Opportunity, and it's not going to have any science instruments. Its job is just to scoot around as quick as it can, several hundred meters a day, like covering ground to go get these samples and bring them back quick. And then you've got the European Space Agency is building the Return Orbiter. That's going to be probably one of the biggest spacecraft sent to Mars. It's going to be huge because it has to get there, break into orbit, maneuver down to the same orbit as the sample canister that's been lofted by, the Mars ascent vehicle, find it, capture it, put it in another capsule, and then come home. That's going to be, I can imagine that easily being $1 or $2 billion. And so programmatically, you're probably talking something between $5 and $10 billion for the whole program.
To return a couple of pounds of rocks.
And you'll probably have a kilogram of rock. Yeah.
Yeah. So priceless is the answer.
That's the thing. Often people say, well, how much would it cost to replace one of the Mars rovers, right? And the answer is, well, can you promise me that you can replace it? If we cut you a check tomorrow, can you promise that 4 years from now it will land safely and do all of this stuff? No, you can't. You've still got risk. You cannot possibly lay down. And so once these spacecraft have got to where they're going, they are priceless. They are essentially irreplaceable.
Wow. I don't know if this is getting a little far afield of your own discipline, but once material like that is back here, I can't imagine how, I guess for lack of a better term, penny pinching scientists would have to be with that material and what they committed to, especially for tests where it wouldn't be viable after it was used or something. I'm sure that they reuse as much as they can, but you've only got so much, right? And I'm sure.
So Destin from Smarter Every Day, he did an amazing YouTube video that's a tour of the Apollo sample lab down at Johnson. And in terms of the Apollo mission was ridiculous. It returned hundreds of pounds of rocks from the moon. But of those rocks, something like 95% has never been touched, right? The vast majority has been kept in storage, and they just trickle it out a little bit at a time when there's a really compelling scientific case to do so. There are missions that are far worse than that. Hayabusa 2, which is a Japanese mission that went to an asteroid, collected samples and came home. It landed around Christmas time. I believe it has 5 grams of sample on it. And that's 10 times more than they were hoping for. They were hoping for maybe a gram, right? It's 5 grams. It's it's like crunching up a pencil lead. That's all you get, right? But literally, you need just a few grains, and there are laboratories that can take it apart an atom at a time to understand exactly what's going on. You don't need a lot to do a huge amount of science with it. And so even just one sample tube of a really nice kind of sedimentary mudstone thing, you could spread that between 100 different labs, and they could all do incredible research with it.
Well, yeah, and there's a lot of stuff that people can do that's non-destructive as well, right?
Yes. Yeah, I mean, the best science typically is it can that's the wrong place for words, but some of the best science is done destructively, but some of it can be just, let's understand exactly what the composition of this thing is. Let's understand not just the elemental composition, i.e. it's got this much iron, this much nickel, this much cadmium, whatever, but the mineralogical composition, because you can take those ingredients, those atoms of various elements, and mix them in different ways. And so your iron and your sulfur can be various forms of iron sulfates that form different minerals, stuff like that. And that mineralogy tells you something about what was going on when it was formed. It's like you've got all the ingredients in your kitchen. That doesn't mean every time you go into the kitchen, you're going to come out with a tray of cookies. You might come out with bolognese, right? And so you can learn more about what was going on when that stuff was made.
It's funny you say that. That's one of my favorite cookbooks of all time is Michael Ruhlman's Ratio, which is basically just a series of ratios for different baking different things. And it's like, bread and cake, basically the same stuff put together in different order and processed differently. And the same thing applies to geology, I guess.
Yeah, it is very rare to find a new mineral like on Mars. A friend of mine, Kim Maxwell, at the time she was Kim Lichtenberg, she did her thesis on a particular iron sulfate mineral, and Kim, if I get this wrong, I apologize, a particular iron sulfate mineral that hasn't been found on Earth, and she just mapped from orbit. It's in a particular part of Mars. It's really interesting about the geological history it could tell us about. Unfortunately, to have the rights to name it, you have to be able to find some on Earth, and so she doesn't get to call it Lichtenbergite until find some on Earth.
So this is one of the things that always strikes me. Are all of your rover people, are you all geology nerds, Doug?
So you know what? Some are really into the geology, and I'm not a geologist, and I understand some of it, and I understand just enough of it to be dangerous, but not enough to be useful. But some people pay really close attention. As you can imagine, a project like the Curiosity team has a lot of meetings, and the various subsystems have, weekly meetings. The whole project has a weekly meeting called the Strategic Mission Planning Meeting. And the highlight for everybody every week is when our project scientist, Ashwin, gives us a report of here's the science we've done in the past week. Because ultimately that's what it's for. Some people will find it rewarding from a purely technical point of view. I know people who are in this purely from a systems engineering point of view. They don't really care about the spacey stuff or the science. They just care about solving really difficult problems, right? That's the angle they come at it. Some of the people, like the let's drive over a hill, see what's next. Some people like if we pull all this together, we could find out if we're alone, right? But everyone enjoys Ashwin's slides of what the science has been recently. And
sorry. So I have a slightly esoteric question off the back of that. So you talk about getting, experimental data and results on a weekly basis. Like, I'm sure, for scientists, it's very exciting, but I assume the average layman would look at it as being pretty mundane data.
Well, when we spent most of Christmas parked in front of a field, like a big field of sand.
Right.
This is awesome.
So setting aside the what I am sure is the impossibility of this question for a second, and just as a hypothetical, let's say that he shows up one week with firm evidence of indigenous microbes that have been found on Mars, something outlandish that basically is proof positive of life. Do you know if there is a plan in place, institutionally, in terms of, and this is maybe a big question, but how that would be handled internally, how that would be messaged like that? I mean, that's essentially the most profound discovery in the history of humanity, right? So how would you handle something of that enormity? Do you have any idea what step one would even be?
So gigantic science discoveries get managed fairly well. If, for example, if we always joke, what if there's a dinosaur bone over the next hill, right? And so a lot of what we do is public the very second it's on the ground. The images we take with our engineering cameras are released to a public website as part of the same pipeline that processes them on the ground when they reach the ground. And so if the timing is right and it goes from with the rover drives, we take a bunch of imaging, it goes straight up to Mars orbiter and then straight from the Mars orbiter down to the ground. If that timing is right, there can be JPEGs at mars.nasa.gov that the public can look at within an hour of those pictures being taken on Mars. And if there's a giant freaking alien sat on the ground, everyone's going to see it all at the same time, right?
And there are communities of people who sit there and just pound refresh on those pages, get the notifications as soon as they change. Yeah.
To be clear, like 8 years ago, that was me, right? And the beautiful images from our color microscope called Mali, MAHLI, Mali. They end up online, I think, a little bit later than that because they take a bit more processing. And then the color images from our cameras up on top of the mast, called Mastercam, they end up online as well. So within a day or two, everything the rover's done in terms of pictures is online. But if we were to make some ridiculous discovery, it's more likely to be through something like the SAM instrument, which is one of our onboard labs, or Chemin, which is the other onboard lab. And the same is going to be true of Perseverance. The kind of epic discovery is going to be through one of the more like squiggly line instruments, and in the case of Perseverance, the two are called Pixel and Sherlock. They're both kind of really they're a bit like SAM and Chemin, but they do it on like a pixel by pixel basis, looking at a rock. They're extraordinary instruments, in themselves more complicated than most spacecraft are.
What's the process for deciding what goes on the what instruments go on the spacecraft?
It's competitive. It's competitive. So like some of it gets assigned. Like you go, okay, we're building a Mars rover. It's going to need engineering cameras so we can get around. So JPL, you're building the rover, go build the engineering cameras. But then the rest of it will go out to an announcement of opportunity. You can Google like the original announcement of opportunity for the payload on board the Mars 2020 rover, and you can see, okay, if you want to be on top of the mast, you're going to get this much power, you're going to get this cold, you can't have more than this much weight or this much volume, whatever. Like the constraints of, I want to be a thing on the end of the arm, I want to be a thing in the rover, I want to be a thing on the mast or whatever. And people will write proposals and say, I think I want to put one of these on it. Now, a lot of the camera stuff was, hey, we built one of these for Curiosity. We think we can do a better one for Perseverance. And so a lot of the color science cameras are upgrades from Curiosity. The instrument everyone loves, which is the laser spectrometer, the pew 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 zap some rocks. We've gone from ChemCam to SuperCam because obviously SuperCam's bound to be better than ChemCam. It's an upgraded version of ChemCam, but it's very, very similar. They're very close heritage. Mastercam is about the same. There are versions of that color microscope that we have as built into part of the Sherlock instrument, so we can still do that. But some of it is like new, and you go, okay, a board will review these proposals for how good the science would be, how much is it going to cost, how much do we trust that they can get it built on time, within the mass constraints, the volume constraints, the power constraints. And they get ranked and they get picked. It's the same way that actual entire missions get picked, like the Psyche, a mission that launches to an asteroid in a year or two's time. That was competed. There were other missions that were going up against that to get picked, and they'll say, hey, we've got $500 million plus the rocket. Who's got some ideas? And the community sent in ideas. I want to land here. I want to fly by this. I want to orbit that. And the best ideas will get kind of seed money, like an extra kind of, typically it's a couple $1 million to really mature that proposal, to make it a watertight mission design. And then those will get competed. So, for example, the Titan helicopter called Titan Dragonfly, there were many proposals for that size. That's like $1 billion mission. There were loads of proposals, and then two got the money to really mature their idea. They were called Caesar. That's a comet sample return mission, and Titan Dragonfly. And Caesar would actually go and visit the comet that the European Rosetta mission was exploring. It would go back to that comet, collect some samples from it, and return them to Earth. And both, like, you have to go, which is going to be more awesome, bringing some freaking comet home or flying around Titan? And it's like, they're both amazing.
Yeah.
We should be able to do both of them. In fact, let's go and bring stuff back from 20 comets and land on everything, right? Like, but we only have so much money. And so you have to say, you know what? Caesar's a really exciting mission, and hopefully at some point we'll get to go and get samples back from a comet. But Titan Dragonfly, in terms of new cutting edge science, in terms of pushing the engineering forwards without kind of ridiculous risk, let's go and fly around Titan for a bit.
Do you think another terrestrial object seems valuable?
Yeah. Could NASA's interplanetary operations scale kind of ad infinitum with more budget, or would you hit another ceiling at some point of like, well, more money is not really going to help at this point? We've got technological hurdles or something of that nature.
There are. You end up with kind of stress points in kind of a whole array of things, like, do we have enough ground stations to talk and listen to all these damn spacecraft? Back in the late 90s, early 2000s, they realized, oh god, there's going to be so many spacecraft in the mid 2000s, we need to build some more antennas. And so the Deep Space Network got some big upgrades in advance of that. And that's actually been happening again recently. Like, I think it was actually yesterday or the day before, we turned on and like rolled out into full use a new 34-meter beam waveguide antenna in Madrid, Spain. Its kind of unveiling was put back a bit by the snow that Spain has had recently, but like that kind of infrastructure stuff. Then you've got to, can we build them? You have various subcontractors. Lockheed Martin has built a lot of spacecraft for NASA. Ball Aerospace has built spacecraft. JPL can build spacecraft from pretty much the ground up, and so there's only so much of that capability around the country. And then there's the money issue. It's like, okay, what can we afford to do? We are entrusted by the nation with a very large amount of money. Planetary science gets, $1 billion or $2 billion per year. It's a lot of money. And it's very easy to look at a mission like Curiosity and go, well, it's only one latte a fortnight over an area the size of Wales, or some other ridiculous, nonsensical metric, right? But very roughly speaking, the Curiosity rover costs each American about $10, right? And on a year-to-year basis, to keep it running, it costs every American about 10 cents, which I don't think is bad return on money. Actually, I think that's pretty good. About a quarter each, roughly, to keep Curiosity going.
Look, I'd rather do that than buy more F-35s, Doug.
I mean, that's one of the arguments is that NASA likes to retain the ability, like within the agency somewhere, and NASA has many centers around the country, to retain the ability to, without depending on a contractor, build a spacecraft from the ground up. And so JPL is one of those places. Goddard is also one of those places. So that if Lockheed vanished tomorrow, we could still build these spacecraft. I mean, that ain't happening. But
no,
yeah.
But it's important. It's important to retain that institutional knowledge. And every time the space agency has stopped doing that, we've had to spend a ton of money ramping it back up and time.
There was a horrific bathtub in the 80s and 90s of planetary science. Planetary science basically dried up in the 80s and 90s, and it was a huge effort to get that back underway. And I hope we never go back to those dark days, because I mean there are planetary scientists who were adrift for a decade, and it must have been like there were basically no Mars missions between the 70s and the 90s. Very roughly speaking. Yeah. And we've not stopped since, which I think is a really good thing, because you can build on what you learn, not just from a scientific point of view, but from an engineering point of view, and so on and so forth. The other thing we've done is that we've almost bifurcated our missions. And so we've got these big things, we've got a giant thing going at Europa in a few years. We've got, Perseverance weighs about a ton. We've also been developing tiny spacecraft. So some of you may remember when the InSight spacecraft went to Mars a few years ago, it actually had two little CubeSats that are kind of briefcase-sized CubeSats called Marco. And no one had sent a spacecraft that small outside of Earth orbit before. And those little guys worked all the way out to Mars, and a couple of weeks thereafter, in fact. And so now, having proven, hey, you know what? It doesn't take a ton or 4 tons of spacecraft and $1 billion to go and do something cutting edge. But actually, if you focus what you want to do enough, $20 million and something the size of a briefcase will get it done for you.
Wow. Well, and it lets it's like packing a couple of things on top of your shipping container from China. It costs nothing if it fits into the mass of the ship the rocket, right?
So like the humongous SLS rocket that NASA is supposed to be launching later this year or maybe early next year with the Artemis 1 mission. The part I'm excited about is the fact it's going to carry a dozen CubeSats. And in terms of like the mass of those things, they are a rounding error in what that rocket can carry. There's SpaceX is launching a Falcon 9 in the morning that's got more than 100 spacecraft on it. And they're all these small, dedicated, like very specific purpose. What's the minimum viable product to go and take this measurement? Planet is basically a huge fleet of CubeSats that do for the entire Earth what the Landsat missions have done in the past. And they're doing it with tiny, tiny spacecraft.
So like, I know nobody wants to have to do more with less, but what you're describing almost sounds like maybe it is the pathway to landing on everything, like you said. I mean, kind of small, very focused and cheap.
Yeah, I think the technology has got to a point where we can do a whole bunch of cool science with smaller missions in more places for less money. But there are still these big questions like, you want a big ass camera flying around Europa to go and map it. You want, like, the James Webb Space Telescope is north of $9 billion. There's no real easy way to get around the fact that the laws of physics say to get really detailed photographs of deep space, you need a big ass lens, right? You need a gigantic mirror. They ain't cheap, right? And so I think you get this bifurcation.
You can't just AI upsample the pictures of things you've never seen before.
Zoom, enhance.
Yeah.
Right. Front cover of Science magazine. Until they fixed Hubble, that's basically what they were doing. Like, there are some things, like the little laboratory we got inside Curiosity, the SAM instrument, you're never going to get that inside a CubeSat because the laws of physics will not allow that. But you can go and answer certain dedicated things, or if you need like infrastructure stuff, like you could have smaller relay satellites around Mars, stuff like that. Little, just like Marco did when InSight landed. And what's really cool about those missions is they can become not just a platform for pushing new technology, they can also become a platform for training new engineers and scientists. And they become the ones who then help go and design the next big, amazing, huge thing. So I know people who were on the Marco project who are now working on Europa Clipper or a mission called Emit that's going to go to the space station, stuff like that. And a mission like Curiosity being, 8+ years in and running on $50 million a year is a training ground for new engineers who are then going to go and operate other spacecraft in the future. I have my engineering camera team is pretty young. And a lot of them are fresh out of college. And, I've been reviewing intern resumes today to have a summer intern on our eCam team to help improve some of our uplink scripts, our downlink scripts, with the hope that, if this person works well, maybe you can hire them in 2 years.
That's amazing. Well, like in terms of science fiction brought to life, the helicopter is pretty high up there. But the other thing that's really amazing to me about Perseverance is MOXIE, the oxygen generation experiment.
It's because the short story is it's ridiculous to take everything with you that you need when you're going somewhere like Mars, right? Lewis and Clark did not take every single thing they were ever going to need to eat all the way across the country.
Yeah.
Mars has a whole bunch of building blocks of stuff. Mars has a lot of carbon dioxide. It's called its atmosphere, right? It has, if you scoop down into the ground a little bit, it has water ice, right? And so now you've got C, you've got H, and you've got O. That's pretty much everything you need to make anything new and shiny. You can make oxygen, you can make rocket fuel, you can make breathable air, right? And so MOXIE is the first step in that of, okay, can we take Mars's carbon dioxide atmosphere and using a pretty small little lab, turn it into oxygen? It's not going to generate, hundreds and hundreds of liters of oxygen, but it's going to prove that a small lab can actually generate oxygen in the Martian environment, breathing in Mars air, not just sticking it in a vacuum chamber and giving it nice fresh carbon dioxide to breathe. And it'll take a lot of power. It'll be a bit like the SAM instrument on Curiosity. Like when we're going to do a SAM instrument experiment on Curiosity, we kind of, in terms of our power story, we kind of brace for it for a few days in advance. We make sure we're fully charged with our battery because it takes a lot of power to run that thing. MOXIE is going to be the same. But as a tech demo, you can then go, okay, this technology now works. We can now scale that up for humans going to Mars at some point down the future.
Well, it's the thing that's amazing to me about Mars exploration. I don't know if this pertains to the Viking stuff in the 70s, but starting in the 90s, like there's a straight through line where there was a new technology, launched with a MVP, right? And then there's a bunch of other, hey, let's see what works and what doesn't. And those technologies that worked move forward on each new generation of probe or rover. And this is just the next step, right? Or the next potential step, I guess.
Yeah, absolutely. Yeah. I mean, like you can look at Curiosity and Perseverance and say they are a direct descendant of the little Sojourner rover from 1997. 6-wheel drive, 4-wheel steering. There is probably deep in the code of the software used to drive Spirit, Opportunity, Curiosity, Perseverance, code that was written in the time of Sojourner, because it's the same problem you're trying to solve. You learn the lessons as you go. Spirit and Opportunity's landing system was directly derived from Mars Pathfinder. Perseverance's landing system is basically the same as Curiosity's, with a couple of fairly modest upgrades. What happens when you kind of stop is suddenly that progression, that institutional knowledge of here's how we go and do landings on Mars goes away. But it's not completely thrown away. For example, if we go and land on Europa, it'll probably be with something that looks an awful lot like a sky crane that landed Curiosity and Perseverance. It will probably be, a sky crane type thing, lowering it onto the ground on the bottom of 3 ropes that looks terrifying in animations, but actually isn't that as scary as it sounds. And is way less scary than what we did with Spirit, Opportunity, and Mars Pathfinder back in the day.
Those were the big balls, right?
Gigantic airbags, like the ones in your car, but way more expensive, as Steve Squires would say. Gigantic airbags. So the landing system for those, like all landing on Mars, big heat shield, that gets you from 25 times the speed of sound to about Mach 2. If you do nothing else, you hit the ground at about Mach 2. That's a bad thing. So you pop out a parachute, big ass parachute, and even the parachute the size of the one for Curiosity, you're still doing 200 miles an hour. And so you then have to solve kind of the last kilometer problem. Is I'm doing 200 miles an hour and I'm a kilometer up. How do I ideally, get to a stop before I'm underground? And so the way Spirit and Opportunity and Mars Pathfinder did it was the back of their entry capsule had some solid rocket motors on it. And solid rocket motors are great in that they are simple and you turn them on and they work, but you can't turn them off. And so about 100 meters before they slammed into the ground at 200 miles an hour, they fired those rockets, and that brings the whole stack to about a dead stop 10 or so meters above the deck. You cut the rope and then you just drop in your gigantic airbags, and then you bounce and you roll and you bounce and you roll. They're looking to
hope you land right side up, right?
So the cool thing is that whichever side you land down, you open that first and the whole thing kind of rights itself. Okay. But, airbags can get in the way. Winds can be a nightmare. Where the Spirit rover landed was only a picked landing site because they figured out how to deal with the winds with that crazy system. With Curiosity, basically it's the same, but they went, what if we didn't use solid rocket motors? What if we use liquid-fueled rockets that we can turn up and down? Then we don't hit the ground really hard in airbags. We could just plop the rover directly onto the ground. And in that respect, it's a lot more sane than gigantic airbags and bouncy and rolling and hitting the ground at 20 G. I mean, the landing of Curiosity on the ground was way gentler than any of the Apollo astronauts landed on the moon. It was 75 centimeters per second. It was a gentle plop onto the ground. Wow. Yeah, it's very, very gentle. And you could say, well, why not put the rockets underneath? Well, you put the rockets underneath, you land, but your rover is still about 2 meters above the surface. And how do you get it onto the ground from there, right? So I would love to have been a fly on the wall at the first meeting where people like Adam Stelzner and his colleagues had to go to NASA headquarters and say, okay, so big new rover, we took a look at the airbags, not going to work, but we've got... Slide one, please. Right.
It seems like the scariest part of the whole thing in terms of problems that you can't fix from Earth is that landing sequence, right? Like if something goes wrong there and the computer doesn't, the rover doesn't pick it up, the rocket sled doesn't pick it up, that's potentially the end. Yeah. Is there other stuff beyond that? I mean, it seems like everything else, like looking at what was done with Spirit and Opportunity, especially over the, incredible lifespan that those little rovers had, you all seem like wizards, is what I'm saying, basically.
We can figure out ways to do an awful lot with not very much. Like landing is probably the hardest part. After that, the riskiest part is probably the launch, because that is riding a bomb for 8 minutes, right? Once we've landed, it's a case of, does everything behave the way we expected it to? And you kind of have to learn how to fly your spacecraft once it gets there. In the case of something flying through deep space, let's say you're sending something to an asteroid, you've probably got 1 year or 3 of cruise you're going to spend flying to your thing. And so you've got some time to get to know your spacecraft and stuff like that. With a Curiosity or a Perseverance, it's a completely different spacecraft for the first 9 months, right? It looks like a flying solar-powered donut, and it's spinning through space at 2 RPM, and it's a deep space spacecraft. And then in the space of 7 minutes, it turns from that into a rover with 6 wheels on the ground, and now it's sat on a big rock that's rotating through space. And that change in 7 minutes, there's so many different configurations of the vehicle. It goes from being this deep space mission into being a fiery entry capsule, into hanging under a parachute, into being a thing that's flying under rockets actively, looking at the ground to figure out where is safe, to then lowering the rover onto the ground, cutting the bridles and flying away. And there are so many things that can go wrong. It's ridiculous how many things can go wrong that give you a bad day. And you cannot simulate it all in one go on Earth, because Earth is so un-Mars-like. You cannot rehearse that entire thing. You can rehearse bits of it. You can simulate other bits of it. You can test the interfaces between all the bits of it, but you can't do it all on Earth because there isn't any way you can go and do it. It's too different. The one good thing that Perseverance has is we've done it once before. That was Curiosity. And so they learn things with the Curiosity landing that they have fed into the Perseverance landing. And the biggest upgrade actually is that the moment it drops out of the back shell to do the powered landing part, the bit where it's actually flying under rockets, just before that happens, it's actually going to take pictures of the ground. It's going to identify features on the ground, look them up in a map it has on board and go, that's safe, that isn't, that's safe, that I'm going to land there. I know that bit to be safe. The geologists on Earth mapped it and said, that's a nice lily pad, I'm going to go and land there. And so when it drops out the back shell, the first thing it will do is fly in that direction and then try and land there. That means you don't have to find like a 10 by 5 mile patch of Mars that's all perfectly safe, which is basically impossible. You just have to find a patch that big that has some safe bits in it that the vehicle can get to, right? And so that's why Perseverance will be able to land way closer to exciting geology, because we don't have to find a gigantic parking lot for it to land in. And then after that, it's like, okay, we thought we knew how we operated Curiosity. We are still learning new cool things we can do with Curiosity 8 years later. Perseverance, like, okay, we think we know how it's going to operate. How's it actually going to behave? How the instrument's actually going to behave when they're not in a test bed at JPL or one of the other institutions that built the instruments. Well, now it's actually on Mars. It's going through daily temperature swings. There's dust, there's wind. You learn how to operate your spacecraft, and that kind of getting to know you phase can last a couple of months with something like Curiosity or Perseverance. And then over the months that follow, they'll get better at operating it. They'll understand it better. They'll be able to do it quicker. And assuming the landing goes well, I'm sure there are no problems that vehicle that can present that we won't be able to figure out in some way. Curiosity, we've got 2 flight computers. We've got an A computer and a B computer. A computer is kind of crappy. The flash memory doesn't really work, but we still got it as a lifeboat if we need it. And we've been on the B computer most of our mission, and it's been behaving absolutely fine. And so the ingenuity of some of the engineers who really understand the systems of the vehicle is extraordinary, getting the absolute most out of a tired old rover. I saw it with Opportunity to ridiculous degrees, and I'm seeing it with Curiosity now. And Perseverance, with a whole bunch of new toys, is going to find a whole new way to use those.
I think let's see. I think so. So the last thing I wanted to touch on, we talked about this a little bit on the Patreon episode, but I after we talked about the Deep Space Network last time, I wondered why we don't just put a big giant radio in one of the Lagrange points that either trails or leads the planet, so that we can talk more.
Yeah, so let's take Curiosity, for example. So we talk to Curiosity once a day. We basically send an email in the morning that says, here's your to-do list, get on with it. And then the way we get data back is in lumps.
Wait, do you guys like Wunderlist or things or something for that? Or like what's your you got bullet journals? What's your strategy there?
It's just a very plain text. The crazy thing is, if you were to actually look at the flight software commands, they're almost human readable. They look like kind of scripting language. The way the flight software has been written is that the way we command the rover is actually abstracted quite a long way, so that when we're planning, one of the steps in that planning is literally reading through the commands one at a time, like a code review. And we all understand.
I'm sorry. I'm gonna have to ask you to just give us 2 or 3 sample command lines.
have to kill you. I will code it enough. I could show you a command to take a picture with one of my engineering cameras, and it would read something like, take an image. It's this important on a scale of 100 is not important to 1 is vitally important. I want you to use this camera and this camera. I want you to point them using this method in this direction. I want you to shrink it or not. I want you to subframe it or not. And then I want you to compress it in this way. Thank you very much. And you could look through those commands and, the subframing, the compression. It makes sense. And it has to be, because unlike deep space missions where, you send up 2 weeks of stuff and you've had 6 months to plan it. We don't know what Curiosity is going to see over the next hill. We don't know what we have to be responsive on a tactical day-to-day basis. And so Mars surface operations broadly and Mars rover operations specifically are very different to operating other deep space missions. So we get our data, we give it kind of a to-do list. It does all that stuff, and then the data comes home in these chunks through these relay passes with the orbiters, like MAVEN, Mars Reconnaissance Orbiter, the Trace Gas Orbiter, and we'll get something between 100 and 1,000 megabits on one of those passes. Typically, depends, exactly where in the sky the orbiter is and stuff like that. We take the last of that data to decide what we're going to do next with the rover. But that data has to make it home, and it gets home from the orbiters down to the Deep Space Network. And we have antennas in Madrid, Spain. We have antennas in Canberra, Australia. We have antennas in Goldstone, which is basically halfway between Barstow and Vegas. And in terms of getting the data home, that's fine almost all the time. There's almost always a ground station that can see Mars. That's why these ground stations are 120 degrees apart around the world. But there are times when we cannot talk to Mars, and that's known as solar conjunction. It's when basically the sun is in the way. And at radio frequencies, having the sun in the way is like kind of trying to whisper across a crowded room. It's the sun is sat there shouting at every wavelength imaginable, and we're trying to whisper our way to a spacecraft, and it's whispering back again, and we just can't reliably decode that data. It turns out generally speaking, we can hear the spacecraft reasonably reliably, but they can't hear us reliably. And so you'd hate to send a command and for that command to be bad and the rover to not know that it's bad and something bad to happen with the vehicle. So we stand down for anything between 2 and 4 weeks. The last time we did it was August of 2019. If you've got an Apple Watch, you can actually change like a planetarium mode, and you can scroll forwards time and you can see when Earth and Mars are going to be opposite sides of the sun. So the next one is this October. And so what we do is we basically give the rover a couple of weeks of stuff to do that's not too complicated. It's collecting a bit of data here and there. It's not driving anywhere. And we send it up a few days in advance to make sure it's on board and happy and healthy. And then we say, okay, see you in a couple of weeks. And it comes out the far end and we pick it up and carry on. Now, you could imagine a situation where you have, and Will has done his homework, a Lagrange point where there are places in the solar system where you can essentially balance a spacecraft in the gravitational influence of, say, the sun and the Earth, for example. And you could park a big spacecraft over there to act as like a middleman, right? Like act as a deep space relay. The problem is that the receivers we need on the ground are so incredibly sensitive. They are cryo-cooled. They are racks and racks of electronics. They are incredibly high-tech. And getting one of those reliably and stably into something small enough you could launch into space would be really, really tricky. We also, so that's receiving the data from the spacecraft. To send data to the spacecraft, we shout really loud. Our smaller antennas typically shout at 20 kilowatts of emitted RF power. And we can turn them up to, like, the bigger antennas, we can run them at 100 kilowatts, even more than that. And it's hard to generate that much power in deep space. Gigantic solar panels on the mission like Juno, which has, some of the biggest solar panels we've ever sent into deep space, would generate something like 10 to 15 kilowatts as far from the sun as the Earth is. And so it would be conceivable that you could develop some sort of spacecraft that would perhaps be able to hear the Mars orbiters, maybe receive their data if they turned their data rate way, way down, and then maybe send that data back down to Earth. But that's a huge investment that's hundreds and hundreds of millions of dollars of spacecraft you've built to go and do that. And all it's really going to buy you is a couple of weeks a year. Now, when we send humans to Mars, you're absolutely going to want that there in advance. Absolutely, because you do not want humans to be out of touch for 3 weeks, because God knows what they're going to get up to on the far side of the solar system, right? We've all seen the Martian.
Brothers and sisters, it's time for the Martian Revolution. I played that video game.
Yeah, right. The time is now, yes. And so you'd want something, and you're not going to. I don't think you're going to have, like, when we finally have people landing on Mars, we probably will have the infrastructure in place at Mars to end up relaying, live video while it happens, kind of thing, and certainly live voice comms from Mars, things like that. You might be able to get low data rate voice comms through fairly modest Lagrange station spacecraft, but generally speaking, like, it would be a huge investment. It doesn't get you a lot more science. So we just give our spacecraft a couple of weeks off. The last time we did it on Curiosity, which was August of 2019, we actually went, some people have actually planned vacations around solar conjunction in the past. Last time we didn't. We actually said, okay, now we don't have to worry about Curiosity for 2 weeks. We're going to do an entire ground data system software update. And we moved from Red Hat 5 to Red Hat 7, and we had to, we had a whole user acceptance test. Curiosity is on the far side of the solar system, not giving a crap. We're all testing all our flight software. We're pretending to write commands for the rover. And so 2 weeks later, when Curiosity came back, we had a massive ground data system upgrade, because that's kind of the only time we have to do that, is when the rover's busy for 2 weeks, on the wrong side of the solar system. And so in some respects, it's nice to be able to have the time to go on a big long vacation or kind of clean house.
I think thank you so much for taking the time to talk to us again.
I'm sorry, Doug. Can I jump back in?
Go ahead.
One last thing. I just wanted to circle back around to a previous question, because I don't think we quite closed the loop on it about like a truly profound discovery.
Yes, we did. Let's say
sorry. No. So, like, if you you were talking about that sort of thing would probably come off of one of the onboard labs on the rover.
So that kind of discovery is going to be one that is eked out by the science team from the data very carefully over time. Let's say let's say the SAM instrument, they did a run and something really interesting came up. The way that becomes public knowledge generally, and a good example is, for example, LIGO discovering gravity waves, or the scientists who thought they found the phosphine in Venus's atmosphere a few months ago, that kind of thing. Mm-hmm. The science team works with their institutions to say, look, we're putting we think we found the thing X. We think we found something really exciting here. We've done all the work we can with our lab. We have done the best science that we can with the instrument that we have and our understanding of how it behaves. A few months from now, this data is going to be public domain. So we need to get it published, and on the day of publication, we will have a big press event to unveil it. Something like this has happened. We all can recite, the Bill Clinton outside the White House talking about that rock that we thought maybe had microbes from Mars in it. There are a dozen movies that have taken that clip and used it. Mm-hmm. And that was a kind of a strong maybe. And they did the best science they could. They put it together in a series of papers that were going to get released in the journal. And the day of release, you do the press event to explain it all. I don't think we're going to have like a, holy shit aliens.pdf, right?
You're not going to get like the footage of like the Martian microbe with the top hat and a cane like tap dancing on the slide, right? Like not quite.
Form on demand.
No chest bursters.
It's going to be eked out from the data we have.
Okay.
And I think what the instrument team that made that kind of discovery would do is go, here's what we found. Here's what we think it means. Hey, scientific community, what do you think? And that's what happened with the Venus phosphine story a few months ago. And the scientific community looked at it and kind of went, we're not so sure.
Okay.
Or, you know what, you might be onto something. And so that happened with Allen Hill's 84001, that rock that Bill Clinton talked about. It's happened with the Venus phosphine story, and I think it'll happen with like the methane story. The Curiosity. I mean, Curiosity's SAM instrument has found methane from time to time. Sometimes there's loads of it, like a cow farted 10 feet behind us, and sometimes there's nothing, right? And we cannot figure it out. We don't know. We cannot figure out a way for that much to appear, that much to vanish. If you have methane on the surface of Mars now, 400 years from now, it should be gone because it breaks down under the UV radiation from the sun. And so there has to be coming out of something. You can make it through geological processes. There's a process called serpentinization, I think it's called, that can produce methane. There can be bugs farting away, right? Producing methane. Or there could be half a dozen cows on the other side of the planet. We've just not seen them yet. And so, the SAM team, all their data is public. Like, you can go to what's known as the PDS, the Planetary Data System, and download all of SAM's data. It's all there. And you can go and see the methane spike in their data and try and figure out what you think it means. I don't think there's going to be a kind of holy shit aliens press briefing, but there may be another increment of, we think we found some tentative biosignature. We think we found something that perhaps looks a bit like a cell wall. We've found something that we can only explain through biology, whatever. And, this is what we think we found. Hey, scientific community, help us out here. We've had those big scientific leaps in the past. We had it with Allen Hill's 84001. We had it with the picture of the black hole. We had it with phosphine at Venus. We've had it with those, we had it with the day they announced they had found the Higgs boson at the LHC, right? Like, those big discoveries get done the right way. And a lot of people quite rightly have issues with kind of the scientific embargo process, whereby some members of the press get the papers in advance and stuff like that. But I think that does give us the media a chance to try and understand the story and then share it all at the same time.
Well, and when we've usurped that process along the way with, cold fusion is the example I always think about,
any day now.
it has backfired almost. Like, the reason we do that is because it's, the more people who see it before it becomes widely public, the more likely we are to find mistakes or flaws in logic or whatever it happens to be. So yeah, it's a good thing. It's a good thing to do that, I think. Doug, I wanted to ask you one more question before we go. So we get wheels on what do we call it? We don't call it the Earth. We call it wheels on Mars, I guess, right? Touchdown. The rovers on what are the team's first priorities after that, and what is that? What are those first few minutes, hours, days, weeks, months to the first? I assume this is another 90-day mission that hopefully will go a lot longer.
So Perseverance has pretty much the same kind of warranty that Curiosity does. It's like 1 Mars year, which is roughly 2 Earth years. And bearing in mind that Curiosity is still trucking along in pretty good shape, 8 years later. So immediately it's we're on the ground. Is the vehicle safe? And in fact, if people go and watch the Curiosity landing very closely, those first few seconds, you have to go and watch like the original live footage, not like the edited highlights. The original live footage, you'll actually see, you'll hear Alan Chen, who was one of the EDL engineers. He would say, Sky Crane has started, which is when the rover is literally lowering on those ropes underneath the rockety backpack. And then you'll see the EDL phase lead, Adam Stelzner, looking at 2 of the engineers in that room. One was the engineer monitoring the little gyroscope inside the rover, because that could tell you which way is up. And another was the engineer monitoring the radios to see if the rover is also still talking to us. And if you listen closely, you'll hear on a different loop, you'll hear someone say Tango Delta Nominal, which was their code to basically have one engineer watching the flight software that had transitioned to Tango Delta was touchdown, right? Tango Delta Nominal. The flight software has transitioned to a nominal touchdown. So the rover thinks it's landed. We're not ready to start celebrating yet because the rover's touchdown have all 3 ropes from the Sky Crane cut. Is the Sky Crane just going to go, screw this, and just slap straight on the back of the rover, right? It does have a bad day. Is it going to try and fly away and then take the rover with it? And so they had a rule. It's like, you know what? After 10 seconds, we're either in good shape or bad shape. And so Adam was looking at those two engineers, and you can watch him looking across the room, and you can see him like asking them to count down for those 10 seconds. And you'll hear them say, RIMU is good. That's the rover's inertial measurement unit. RIMU is good. And UHF is good. And only after 10 seconds of that does he turn around, stab Al Chen in the back. And Al, who is the voice of the spacecraft, can then go, touchdown confirmed. We're safe on Mars. What I thought was a lovely sentence he then said that was lost in the cheers was, it's time to see where our curiosity can take us.
Oh,
which is a lovely line. It was such a nice line. And so a similar protocol is going to be in place. Like, okay, the rover thinks it's landed. Are we sure? Right? Because we're going to be getting the same kind of data home, like a trickling like 8 kilobits per second of data on, you really don't get much information. It's what we got with InSight. It's like altitude, heading, temperatures, pressures, voltages, nothing sexy, but enough to tell you if you landed successfully. First thing the rover's then going to do is wait a little bit, let the dust settle down, and then, just like with Curiosity, take a picture out the front, take a picture out the back, and then send them straight home as a tiny thumbnail. And if we're really lucky, as we did with the Curiosity, as we did with InSight, we might well get those thumbnails down within that same communications pass that's still happening. We time the landing not just to be in the right space at the right time, but also to be under one of the Mars orbiters while it's happening, so the orbiter can relay the data home in real time. Like the corner you have to get into in solving all those timing problems is very, very small. So maybe
the orbiters take pictures as well while this is all happening?
It may well. So the Reconnaissance Orbiter has tried to take an image of the landing. It tried with Curiosity and got a hit. Actually, got a picture of it hanging under its parachute. There were a lot of memes of, sorry, my Martian spy satellite was too busy taking a picture of my 1-ton Mars rover hanging under a parachute on another planet, kind of thing. We tried again with Phoenix. We got it. Tried again with InSight, and they missed because the landing ellipse was a lot bigger for InSight, and so literally you can just be pointing in the wrong way. They've probably got a better chance with Perseverance than they did with InSight, and so we may get that picture, but that picture takes a couple of days to get back. Yeah. And then the orbiter will then set, and the spacecraft's on its own for a few hours, and so you have a little bit of data from immediately after landing, maybe a thumbnail or two from the front and the back of the cameras. And then a couple of hours later, another communication pass is going to happen, and the engineers can then really knuckle down and go, okay, how healthy is the vehicle? Is the power supply generating the power we expect? Is the temperature as warm or as cold as we expect? Very basic housekeeping. And then the first few days, you very gingerly say, okay, let's deploy the camera mast and get the cameras up and have a look around properly for the first time. And then it's, okay, let's exercise the robotic arm for the first time. Let's use each of the scientific instruments for the very first time. It's kind of a characterization and checkout phase that can last a couple of weeks. And in the case of Curiosity, we did a big flight software update because the flight computer didn't have enough room for all the landing software and all the surface operations software. So there's that flight software migration as well. And then it's like, hey, let's drive for the first time, And so it's super intensive because when you're doing it for the first time, you want to make damn sure you're sending good commands to your vehicle. And so the planning can take 18 hours, right? And you're working on Mars time. You are working the Martian night shift as far as the rover is concerned. It sends you data back home in the afternoon. You have until the rover wakes up the next morning to make sure you've got commands ready to tell it what it's going to do the next day. And so you go to Mars time, which doesn't give a crap about Earth time. It slides 40 minutes a day, roughly speaking. It's like a permanent state of mild jet lag. And they'll do that for about 90 days. And within those 90 days, one of the things they're going to do is deploy the helicopter and do its test flight program. That's hopefully within those first 90 days, hopefully within the first month, probably. And then you understand how the vehicle works. You understand how the team works. On top of all of this, these guys have got to do most of this remotely. They refurbished the whole building to be their mission planning area, and very few of them actually get to use it because of Corona. You're all on web conferencing software rather than in a room together. That has a level of challenge that they weren't prepared for. And so that learning how to operate the spacecraft, how to operate the team may take a little bit longer than usual. But then you settle into a rhythm. At the 3-month mark, you kind of give up the Mars time and you kind of work basically when Mars time and Pacific hours line up well enough. You operate the vehicle every single day. And when they don't, you operate it kind of 2 days in a go. And then you settle down so it's just 5 days a week, when it lines up with Mars time. And they'll be at that phase kind of at the end of the first year or so. And then what is amazing is they'll have just got going, and suddenly the end of the prime mission, those first 2 years, they'll be screaming down on them. And so it's like, we need to have got a whole bunch of stuff done by the end of our prime mission. We said we were going to have samples on the ground over here. At that point, we've got to get it done. And so at some point, there'll be this focused effort to, we know how this thing works. Time to up the pace. Time to, let's make some ground here. We had that with Curiosity in kind of the end of its first year through the second and third year. It was like, we need to get this damn mountain we've been talking about for years and years and years. Let's get there, shall we? And then the number of people on the mission will slowly roll off. The people involved in that early commissioning phase will roll off onto other missions, and people better at just doing mission ops will roll in and backfill them. And then you're kind of in for the slow cruise. And then the science team starts having data from those amazing instruments and is trying to put together those first papers with those first scientific results. And so the science team is split between operating the instruments every day and doing the science with the results every day. And it's very easy to burn out. It's very easy for all this to become too much. And particularly with Corona, it can be just hard to just be, set a conference to death and still not have time to look after yourself. The fidelity of communication across video conferencing is so, it doesn't seem like it's lower, but it's so much lower when we've done it 5 times in this episode where we're talking over each other and nobody realizes until you're already halfway through a sentence. When I'm training new engineering camera people on Curiosity, I have used the phrase "read the room." Can't do that over WebEx. Doesn't work. Yeah. You can't tell. You can't look over your shoulder and see how the rover planners are doing when it comes. You can't look over and see how the science planner is doing or the tactical uplink leader is doing. You can't see if the rover planners are kind of stressed and you're like, you know what? I'm not going to ask for that extra thing today. Today's plan is already fat enough. I'm not going to push my luck. Let's just, let this one slide for today. We'll try and do that tomorrow, whatever. You just don't get that gut feeling under WebEx. I mean, today, actually, one of the former trainees, Taryn, is on shift at ECAM on Curiosity today. Today, we're planning Sols 3010, 11, and 12, I think it is, which represents exactly 10% of Curiosity's mission will have been planned remotely as of today. Wow. And I am incredibly proud that my little ECAM team has carried on with almost without skipping a beat. And incredibly proud to be part of the whole mission team that has managed to not just keep the lights on, but keep the rover busy, scientifically productive. There is nothing this rover can do that we haven't done remotely. That our first fully remote shift, which was, he said, looking at the calendar, March the 20th last year, was our first full remote uplink shift. We drilled a freaking hole on Mars. That's the most complicated thing our rover can do, is drilling a hole. And we've since had another drill campaign, then a really crazy focused drill campaign where we did 3 drill holes in one rock and we ran them through every lab multiple times. And then we've had a phase where we were kind of sprinting as far as we could to get to some big sand dunes we wanted to study over Christmas. We did that. We're now sprinting our way again. Meanwhile, we did a flight software update on our backup computer. We're working on a big flight software update for the whole rover for a point in the future. We're figuring out how to operate the vehicle on less power because our power story never gets better. It's only ever going to get gradually worse over time. Can we operate the rover more efficiently? Can we do more stuff in parallel? I've trained 3 people remotely to operate the engineering cameras. We didn't even think that was going to be possible. And just like with a degraded rover, we figure out how to make it do cool stuff with a degraded, for want of a better phrase, world. Sure. Right? Yeah. We figure out a way around it and make it do stuff. I do not envy. I'm a little bit jealous of the Perseverance team getting to, be, Sol 1, let's do cool shit together. But I'm not envious of them having to try and wrangle, especially those with families, trying to work Mars time with a family, but you still got to work from home, like trying to find a corner of the house where you can be doing your office work from like 11 p.m. till 10 a.m. It's going to be really hard on families.
Family doesn't understand that you have an extra hour in your day because you're sitting right next to them.
Like California homes aren't really set up for this kind of remote working either.
They're really not. I mean, and we just crossed Sol 3000 with Curiosity. As with all these big milestones, someone designs a logo and we all get a link to Land's End where we can go and get it put on polo shirts. He said, pointing at his polo shirt. And we make, like with Curiosity, we make damn sure there are 2 links. There is a link for team members to go and order stuff for themselves. So it says MSL Flight Ops Team on your shoulder. And there is a link for people so you can go and order a shirt for your spouse, your kids, your grandma who's looking after the kid, whatever, because they're a part of this puzzle too. Like, I couldn't do my job on the day-to-day without, my family around me, without my wife helping out, without her family helping out. The joke, and we've made it many times, is that we're only working ever so slightly more remotely. It's 200 million kilometers. What's an extra? But it feels a lot further away, and to be doing the Mars gig from home isn't easy on anybody, especially for the Perseverance team who are going to be on Mars time. I know some of them will be going into work. They'll be masked up, they'll be doing regular testing and stuff like that. And so they got the stress of, being in the same room as other people and stuff like that. It's really, really hard work. And
all this and don't touch your face too. Good God. Right?
Yeah. And I mean, the worst part of all, if you go and watch the Curiosity landing footage, is 2 people desperately trying to high five each other, and they just kept missing, and we won't get to see that when Perseverance lands.
The secret is to look at the other person's elbow. Yes. It turns out that's you just look at the elbow and then boom, it's really straightforward. But
I have actually trained people on how to do good high fives in case they found themselves in a live on CNN situation with a $2 billion space. I'm like, dude, this is how you do a high five in a high stress situation. Look at the elbow and go for it, right?
Yeah, I was gonna say, if you want if you need a high five consultant, I have done videos on the internet about how to high five effectively. So. For a nominal fee, I'm happy to come down anytime, Doug.
Once the Rona is over, you can come down and give us all a seminar.
Yeah, we'll do a high five lessons. Like Norm and I even did a running, jumping high five on a high speed camera it tested back in the day that only injured one of us twice. So I think on Brad, unless you have anything else on that note,
that does it for me.
Doug, thank you so much again for coming in and answering our inane questions about this stuff.
It's an absolute pleasure. There are no inane questions about Mars stuff. It's all pretty cool and exciting, whatever angle you come at it.
Cannot thank you enough for being so gracious with your time, especially on a Friday evening.
It's an absolute pleasure.
And I guess that'll do it for us this week. As always, thank you to our fabulous TechPod patrons. As always, you can find out about the Patreon at patreon.com/TechPod, where you can get access to the fabulous TechPod Discord and talk to people like Brad and me and Doug and a bunch of other wonderful nerds.
Yes. And hear Doug's previous appearance. I hate to sound like I'm trying to upsell here, but please subscribe to our thing. But yeah, Doug's previous episode was a patron exclusive, and like we got into some of the topics we touched on here in a lot more depth about like VPNing to a Mars rover and a lot of other interesting stuff like that. So if you like what you heard here and want to hear more, that is there waiting for you.
And as always, thank you to our executive producer tier patrons, the Bunny Fiend, Jacob Chappell, David Allen, and James Kamek. You all rock, and we appreciate you and everyone who subscribes to the Patreon. I think that'll do it for us this week. We'll be back next week with another episode of Brad and Will Made a Tech Pod. See y'all next time. Oh, wait. We didn't do plugs. We got to plug. Doug, do you have anything you'd like to plug?
Pay your taxes.
Okay.
Go.
Look, I was contemplating a tax revolt until about November 8th or 6th. I can't remember what the exact day was, but so yeah, okay. Well, I'll pay my taxes next year, I guess. Thank you again.
Same.
See you all next week. Bye, everybody.